Okay, so as promised, these are your lecture notes for the second week of the New Jersey Seeds Capstone Experience. Today we're going to be talking about force, okay? To start with, a force is a push or a pull, okay? You experience forces every single day. The most common force that you probably experience that you think of off the top of your head is gravity, okay? I'm holding the marker in my hand right now. We know that the force of gravity is trying to bring this marker to the ground, okay? But right now, something is preventing that marker from hitting the ground. What's preventing it from hitting the ground is my hand. My hand is supplying an upward force to keep the marker from hitting the ground, all right? This is a wonderful diagram. I know, I'm an artist. This is a wonderful diagram of a person who is standing on the floor, just as I am right now, okay? As I'm standing here right now, there is a force of gravity that's trying to take me through the floor. If the floor wasn't right here, I would fall, okay? However, the floor is there. So that floor is pushing up on me and preventing me from falling to the ground, okay? So here I have the downward force of gravity trying to bring me to the ground. And then I have the force of the floor holding me up. We refer to this as a balanced set of forces. The force from the floor is equal to the force of gravity. So one force is trying to take me down, one force is trying to take me up. They are equal and opposite, so they are balancing each other out. That is keeping me from moving, okay? So the total force on me is 0 because the force down from gravity is being counteracted by the force of the floor up, okay? Down here we've got another example of this, another wonderful diagram if I might say so myself. We have a block that I am pushing with two forces. One force, F1, is pushing the block to the right, and then the other force, F2, is trying to push this block to the left, okay? Now there's three different scenarios that we have to talk about over here. The first is if F1 is equal to F2, if both forces are pushing with the same amount. If both forces are pushing with the same amount, they are once again balanced, the same way they were balanced up here when we were talking about gravity and the floor. If we have balanced forces, then this object will not begin to move, okay? It's like you pushing from one side, your friend is pushing from the other side, you have equal strength, so the block will not move. If F1 is bigger than F2, so this is a greater than sign. If F1 is bigger than F2, that means that F1 is going to win and push the block to the right. F1 bigger than F2 pushes the block to the right. If F2 is greater than F1, that would mean that the force pushing to the left is greater than F1. That means that this object will begin to move to the left. Again, you guys already know a great deal about force, but you haven't had anybody explain it to you using actual physics terms just yet, okay? So whichever the bigger force is, that's the direction the object is going to move. If all the forces balance each other out, then the object will not move. That's the example up here with the person, me, standing in front of you, gravity down, floor up, or down here, F1 pushing to the right, F2 pushing to the left, they are still balanced and prevent this object from moving. Okay? Moving on. Newton is the really, really smart guy who gave us our basic understanding of Newtonian physics. When you are so smart that you come up with physics, you get to name it after yourself. Newtonian physics, named after Sir Isaac Newton. And Newton gave us 3 laws of basic Newtonian physics. The first is known as the law of inertia. The law of inertia tells us that an object in motion stays in motion, or an object at rest tends to stay at rest, okay? So let's go back to the example we started the lecture on, okay? Marker in my hand right now. It's not moving, correct? In order to get this to start moving, I need to apply a force to get it to move, okay? That's what causes the object to move. It wants to stay in my hand, okay? An object at rest tends to stay at rest. I need to come over and unbalance it in order to give it to move, okay? This works the other way. If an object is moving, It requires an unbalanced force to get the object to change its motion, okay? If I start throwing this marker across the room, something has got to cause it to stop moving. In this case, I throw the marker, the board applies a force to the marker and keeps the marker from moving. Another example, if you're driving a car and you need the car to slow down, you need to apply the brakes in the car to get the object to slow down. That goes against the law of inertia, okay? If you want to get the car to speed up, you need to apply an outside force to get the car to speed up. So again, first law is the law of inertia. An object in motion tends to stay in motion. An object at rest tends to stay at rest. Next law, force is equal to mass times acceleration. Force is equal to mass times acceleration. Now, mass is going to be measured in kilograms. Mass is going to be measured in kilograms. Remember, we're using the metric system. The acceleration is in meters per second squared. Meters per second squared. And a kilogram meter per second squared, again, he was really famous. He got to name things after himself. He decided to call that a Newton, or big N. Okay? So all forces are measured in newtons. 50 newtons of force, 100 newtons of force, 1,000 newtons of force. Those forces are measured in newtons. So the second law just says that force is equal to mass times acceleration. If you recall from last week, acceleration is the change in velocity. The change in velocity. So if an object's motion is changing, if the velocity is changing, there has to be an acceleration. And if there has to be an acceleration, then that must mean that there is a force, okay? That's why I had somebody in each class come up, and remember when we were doing the example, when we had a velocity pointing to the right, and then I had an acceleration also pointing to the right, and I had somebody from each class come up and push me in the direction of the acceleration. You can now think of that push as a force. So if I'm walking to the right and somebody pushes me to the right, then that's going to speed me up to the right. If I am walking to the right and somebody pushes in the opposite direction, that's going to slow me down. So when you apply a force, you are changing the motion of the object. Last example right here is the action-reaction law. This is the one that students struggle with the most, action-reaction. For every action, there is an equal and opposite reaction. What does that mean? If I come over here and I punch the wall, ow, that actually hurt a lot more than I thought it would. If I punch the wall with some force, the wall is going to punch me back. That's why it hurts, okay? If I come up and punch the wall with 50 newtons of force, the wall is going to punch me back with 50 newtons of force, okay? I can't violate action-reaction. I can't violate action-reaction. So if I come up here and punch it with 1,000 newtons of force, it's going to punch me back with 1,000 newtons of force, okay? Now the reason why students struggle with this, okay, I'm going to give you one example on this video, and then when I see you again next week, we'll talk about the other example, okay? First example, okay? So I come up here, I punch the wall, ow, 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 ow. I can punch that wall real hard, okay? What happens if I try to punch a piece of paper? Ow, 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 ow. It's not nearly as impressive when I try to punch the paper. I know punching the paper isn't going to hurt as much as me punching the wall. The reason being, I cannot violate action-reaction. So the wall can push me back with a lot of force because it's a freaking wall, right? But if I try to punch the paper, if the paper can only hit me back with 10 newtons of force, it doesn't matter that I can punch the wall with 1,000 newtons of force. If the paper can only punch me back with 10, that means I can only punch with 10. So we cannot violate action-reaction, okay? As I said before, I will go over another example of this next week. The first person to remind me about the car bug problem at the start of class next week, you get some extra points, okay?